Okay, I know. Day 2, everybody's tired already because of you all played baseball last night. So, hi, I'm Fred Chuck. I'm the Executive Director of GMA. I'm going to do some introduction here in a minute, but I've got, where's Sam? Sam, I want you to give a little quick introduction about IGS. Sam Allen.
Good morning, everyone. On behalf of the International Geosynthetic Society, and being a proud member of the Geosynthetic Institute and the GMA, I am honored to be present at this prestigious Koerner lecture. I was just at the GSI last week, and I was reminded again of how so many of our lives are affected and have been benefited from the Koerner legacy. And this Koerner lecture, to me, is the perfect anchor for a strong and relevant GMA. And I add my congratulations to the deserving presenter this morning, Dr. Shobha Bhatia, whose leadership and contributions in the field of geotextile pore size measurements has been so important to the technical journey of my own company, TRI. Thank you, Shobha. And I'm also very pleased this morning to inform you that the IGS is now working in a closer way with the GMA. As a learned society promoting our technical membership for industry education, it's not always appropriate to adopt a pure advocacy position. In addition, while the IGS is international in reach, all lobbying, by definition, is regional and local. And lobbying is so important to the continued acceptance and use of geosynthetics. And it's for this reason that the IGS and the GMA and AEGM and ABENT in Brazil must work closer together. And the IGS with the GMA signed a memorandum of understanding at the Geo-Americas conference last year, inviting our organizations to work closer in new and more effective ways. The IGS knows the importance and the relevance of the GMA and fully supports its mission and looks forward to working closer together. Thank you for this opportunity. Good morning. Thank you.
Welcome to the 2025 Dr. Robert M. Koerner Lecture. The Dr. Koerner Award was established by GMA in 2016 to honor Dr. Koerner's impact on the geosynthetic industry by also acknowledging the impact of others in the industry in North America. A committee comprised of GMA Executive Council members selects the award recipient who will have had a measurable impact on the geosynthetic industry, a background in education or testing of geosynthetics, and has worked with or for a geosynthetic manufacturer in North America. Dr. Koerner founded the Geosynthetic Institute. Bob held his PhD in geotechnical engineering from Duke University. He authored or co-authored approximately 700 papers on geosynthetics and geotechnical topics in journals and at national and international conferences. I met Bob 43 years ago while he was assisting Mirify to develop the technical data for our introduction of our product Mirror Drain. And it was my privilege to know Bob for 38 years as we watched the industry grow to the point today where we annually ship close to over 1 billion square yards of geosynthetics in North America. Our first 3 Koerner awardees are here in the audience today. Dr. George Koerner was our first lecturer in 2017. The 2019 awardee was Dr. Barry Christopher. Ji Han was our 3rd awardee in 2021. Our 2023 Koerner awardee was Dr. J.P. Giroux, who provided a live feed lecture from his home in France and may be listening in on the live feed today. So help me thank our past lecturers with a quick round of applause. With that, let me call on Brian G., the chairman of the GMA Executive Council, to introduce the 2025 awardee.
Good morning. It is my privilege today to introduce Dr. Shobha Bhatia, the recipient of the 2025 Robert M. Koerner Award, to deliver this year's Koerner Lecture. Dr. Bhatia's list of accomplishments and accolades in the field of geosynthetics is so extensive, I found it a difficult task to write an introduction which would leave enough time for the lecture, so please forgive my inevitable omissions. Dr. Bhatia received her PhD in civil engineering in 1980 from the University of British Columbia, Vancouver, Canada. She is the Seinfeld Scholar, Laura J. and L. Douglas Meredith Professor, and Professor of Civil and Environmental Engineering at Syracuse University. She was appointed to serve on the National Committee on Geological and Geotechnical Engineering of the National Academies from 2016 to 2018, and has served as a member and in leadership positions of several committees of the ASCE Geo-Institute, the International Geosynthetic Society, and the American Society for Testing and Materials. Shobha is currently serving on the editorial boards of 3 journals: Geosynthetics International, Indian Geotechnical Journal, and the International Journal of Geosynthetics and Ground Engineering. Her early research focused on soil behavior during earthquakes and investigated ways to mitigate earthquake damage to buildings and infrastructure. This work led to her further research on soil imaging and simulation and the use of geosynthetic materials in engineering projects for safety and longevity. She pioneered research on the use of geotextile tubes not only as containment systems, but as effective filters for a variety of dredge sediment and fly ash and mine tailing slurries. In her current research, she is investigating the use of bio and synthetic polymers to stabilize mining waste and investigating rheological and flow behavior of mine tailing slurries amended with biopolymers, preventing damage to the environment and loss of life. Recently, her work was cited in the UN 75 Sustainable Engineering in Action report, and in 2020, she was recognized as a geo-legend by the American Society of Civil Engineers for her contributions to the field. So, ladies and gentlemen, please join me in welcoming the presenter of the 2025 Robert M. Koerner Lecture, Dr. Shobha Bhatia. Absolutely, congratulations.
This is most important. So I understand that Dr. Koerner started his day very early in the morning, as I believe. So it's most appropriate to have Koerner lecture at 8 o'clock rather than 5 p.m. First of all, I'd like to thank Fred Chuck and Brian Gee and GMF for this honor of giving Koerner lecture today, this morning. I would also like to thank Brett Keeler for a wonderful interview. I think more of my students saw that interview than this lecture, probably. And Barbara Canet for many, many years working with geosynthetic conferences and all the help, including this chair she provided this morning for this lecture. It's specifically a great honor to be included in the list of previous Koerner speakers, Dr. George Koerner, Dr. Barry Christopher, Dr. Jihan, who are right here, and Dr. J.P. Giroux. Now, Dr. Koerner, as a faculty member, I recognize Dr. Koerner's contribution in 3 different categories. One is excellence in research, excellence in teaching, and collaboration and mentoring. And if you look at the chat GPT, that also acknowledges his contribution in these 3 areas. So let's talk a little bit about Dr. Koerner. So Dr. Koerner's research, as a researcher, he had around 995 publications, 5 short of 1,000 publications. I don't think that included white papers. And he has written white papers in every possible topic, and my career has been influenced by those white papers. His contribution to teaching is really one of the wonderful contributions is his textbook. And I know this textbook is only textbook which I know has decreased in prices over the time. And when I teach geosynthetics, students are just astonished that they can get a textbook free. So this has been translated in many, many different languages. Now, third part of faculty career is generally we talk about collaboration, mentoring, and service, and we can group that all in one category and one part, which is GSI. I think he has set a stage or set a highest standard of collaboration and mentoring, which he provided to his students, not only his students, but all of his colleagues. So I'm going to use these three strengths as a researcher, as a teacher, and talk to you about my journey as a faculty member at Syracuse University. So my research in geosynthetics started when I took a short course with Dr. Koerner in 1988, and it was one of the ASCE meeting. I just got a tenure at that time, and I was looking for new areas of research. And I just established an image processing lab, and I'm working on a soil filters. So I go to the short course. I had never heard about geosynthetics, and it was a half-a-day course. And one thing smart I did bring a sample of geotextile with me, because he said that this can be used as a filter. And I was working as a soil as a filter. I said that would be very interesting. And this is the starting of my journey and my students' journey in geosynthetics. After that, in many conferences, I met with Dr. Koerner for a short time, but even in a few minutes, you know that he is really listening to you. And when he asks, how are you doing, he meant it. And he would say that you come to GSI, use the equipment. He wrote a letter of support from one of my first NSF grant. So when he asked something, and he truly cared, and I really appreciated that. And 2004, Dr. Koerner came to Syracuse University and gave a local ASCE lecture. He's there in the first picture with my student in my lab where I was doing work in soil filtration. And 2016, with Grace Swan and Dr. Song, we did a specialty session at a Geo-Congress. And I remember clearly the day after when we were checking out, I met him at checkout counter, and he thanked me. And he introduced his grandkids to me, and it meant a lot for me. And I always will treasure that moment. So here is my journey as an academician, and I'm going to use three strands: research, teaching, and collaboration. They are all intertwined. They cannot be separated, because that's what we do. So I'm going to talk to you in next 46 minutes about this journey of geosynthetics. This journey, I'm going to focus only on geotextile, although I have done work on roll erosion control product, little bit geogrid and geomembrane, and this journey is only about geotextile as a filter. Now, before I start this journey, I will acknowledge there are many contributors: Dr. J.P. Giroux, Dr. Koerner, George Koerner, Barry Christopher, and Dr. Holtz, who have done significant work in soil and geotextile filter. But today is my chance to talk about only my journey and journey with my students on a geotextile as a filter in a many, many different applications. So in this presentation, I'm going to talk about a little bit about difference between soil filter and geotextile filter. That's how I started. I'm going to talk about some of the filter criteria and how they differ when the soil, which is in touch with geotextile, changes. And I'm going to spend some time on talking about geotextile tube as a filter. And then few case histories, because case history really allows us to check the value of our research. Sometimes we go carried away in one direction. When we work on real project, it's a wonderful check. Now, geotextiles have been used for more than 50 years in numerous applications as an edge drain in earth dams and landfills and so on, and they have performed very well. And one, I won't say it's the newest application, but fairly new, is geotextile tube, where instead of soil, we pump slurry next to the geotextile. So in my presentation, I'm going to talk about some of these different applications. Now, when I started the work in geotextile, because I was working as a soil as a filter, this image which you see is really a cross-section of a soil sample, which is Ottawa sand, and next to that is a non-woven geotextile. They are not at the same magnification, but not that far. And one thing which I want you to notice that all the black spaces in sand, which is Ottawa sand on left-hand side, those are pore openings. And on right-hand side is a cross-section of non-woven geotextile, and all the light gray area is a pore space. So you definitely notice that porosity of geotextile, particularly non-woven geotextile, is much, much larger. It can be as much as 90%, where typical porosity of soil can range between 30 to 40%. So then you wonder that how would this thin, open textile will work as a filter? Okay. We have done work in our lab, so we learned that geotextile alone doesn't work as a filter. It has to establish a filter zone and bridging zone. Once it is established that, then it works effectively as a filter. And geotextile filters criteria, design criteria, are very similar to soil filter, permeability, retention, except clogging is more of a concern of geotextile filter, although soil filters do clog. Okay. Now, there are over 30 or 40 years, there may be 60 or 70 different retention criteria which have been proposed by lots of researchers, and they include flow of water, whether it's a steady state or non-steady state. It includes soil properties, and most importantly, it includes pore size distribution or pore size of geotextile, which is different. So now we have to really know how to measure pore size or pore size distribution of these geotextiles. So I'm going to take you for 10 or 15 minutes talking about pore size of geotextiles. There are many standards. The first three I list here: dry sieving, wet sieving, and hydrodynamic sieving. These are three standards used in US, Canada, and Europe. They are sieving techniques. And more recent technique is called capillary flow parameter, which also can measure the large pore opening of geotextile. So let me talk to you a little bit about these techniques. These are three sieving techniques. None of them are perfect. Each of them has limitation and some advantages. But one thing I want you to remember, each of them can give you different pore opening size, okay? So they are not exactly, even if you do test perfectly. Whereas capillary flow parameter is a device, and this is a little bit long journey. I'm going to take you a little bit a detour. So we started working with a company in Koerner, not too far from Syracuse. And when I went to this company, it's called Porous Media Incorporated. They specialize in measuring pore spaces of materials. So I took geotextile there. I went with my students, and they had this capillary flow parameter. I learned that most of the samples they are using it, they are pore opening of 2 micron, 1 micron. For them, 5 micron was very, very large opening. So here is, I go with Geotextile, which has 200 micron opening, and they said, why do you need to measure anything out of that? So I learned a lot, and over the time, from 1996 to 2017, my student and I have gone to Cornell on numerous times, learned different devices, they changed different sensors, and we have used the generation of capillary flow parameter. Okay. This is a device, tabletop device. It looks very simple. Test is also done in a short period of time, but it is also very sensitive. And I'm going to show you some results. The latest version of the device, which I have in the lab, you take a small piece of geotextile, you saturate it with a liquid, and then you allow a pressure gradient to establish across it, and you literally see a bubble coming out of the largest opening, and you measure the open pore size, not only large pore size, but pore size opening distribution. Here are a typical test results from one nonwoven geotextile, and you can test 8 or 10 samples in a day, so I think that's wonderful. But there can be problems where the sample is not fully saturation, there's a little drop in the pressure, and so on. So one has to be still careful what you get out of this test. It seems like I have done significant work, sometimes I wonder why, on pore size distribution of geotextile. The study started in 1996, and then 2007, 2009, 2017. And I'm not going to show you all these results, okay? So I'm going to show you one set of results from a study of 2096, and then one set of results of 2017. When we started the work in 1996, we used 6 different techniques to measure pore size distribution of 28 different geotextiles. So let me show you the result of one geotextile. And these techniques were sieving techniques, all 3 sieving techniques, bubble point techniques, mercury intrusion, and image processing. And what I note here, I would like you to note, I'm giving you only the largest pore opening, which is 0.95 of a geotextile. As you can see from this figure, they are very different from different test techniques, and particularly from mercury intrusion and image processing. And after this study, we haven't done the work on mercury and image processing, but we continue to do the work in other areas. More recent study, 2017, included 51 different geotextile. I think we just had many geotextile from US, Canada, and Europe. And they were woven, non-woven, and composite. And we used extensively ASTM standard to measure the bubble point or pore size opening. And here is a relationship, which I think important for us to see. And on one side of this axis, I am plotting here bubble point, which is large pore opening 0.98. On vertical axis, dry sieving results of 0.95 are plotted. And here is the data for 52 different geotextile. Now, question comes, why is this important? Why should we even worry about this kind of data? If we are going to move to a newer technique, which is not new anymore, but bubble point, and we do that test and measure the pore opening, we need to remember that most of the retention criteria which are available are based on dry sieving test results. So if we are measuring 0.95 or 98 from bubble point, to use those relationships, we need to know how much is there really from dry sieving. So this data gives you some idea, and I think this is an important to keep in mind. Now, this is where judgment time comes. So this is a very interesting case history. Several years ago, I received a phone call. I think one of my former students worked in that particular company. And this is in Utah somewhere. And they were building, a company was involved in building a tunnel liner. And contractor placed a non-woven geotextile as a temporary liner. So when the project started, they found a lot of fines were coming through the textile. So they stopped the project. And I received the call. They said, we are thinking about 3 different geotextiles, and we want you to tell us which one will be better. Okay? So this was a perfect timing. We were doing all kind of measurements. So you can see in this table, we conducted all the tests, and we measured the pore openings of the geotextile. Now, next step, we picked up some retention criteria. And the 4 which I show you here, these are Dr. Giroux's criteria, Carroll criteria, Barry Christopher and Holt's criteria, and we also did work, so our own criteria. And if we just use these 3 geotextile, their dry sieving results or hydrodynamic sieving result, I want you to look at this, the green box. It shows that 3 of the criteria says that geotextile selected, like D4, is failed, means should not use it. And where if you use the FOS of the same geotextile, which is a different number, then out of 4, 3 criteria says it should be passed, okay? Now, if we stop here, then I don't know what is the answer, because it depends which value you use it. So we go a step further. As a geotechnical engineer, we all love FlowNet. Students don't, but we love FlowNet. So we drew FlowNet and calculated the hydraulic gradient, which would be at which water will be flowing. And then we conducted a long-term filtration test. So the company has sent us silt. So we put in our filtration test next to each of the geotextile soil at around 45% water content and performed the test for 24 hours at hydraulic gradient of 4 or 5. It seems like all 3 geotextile worked very well, and then we increased the hydraulic gradient to 10. And you can see one of the geotextile, suddenly there's a jump, and a lot of fines came out of that, which means for this geotextile, filter cake which was formed was not stable. So based on that result, we recommended either of the 2 remaining geotextile should be used. We never heard back from the company, but we received a thank you note and a check. So I think the project was successful, okay? Now, this is, I'm just moving next to the soil instead of soil. Now, next to geotextile, we have a slurry of high water content. And I want you to look at 2 slides on the right-hand side. In one where the long-term filtration test, the water content is around 30 to 40% of the soil. And the bottom one is where the water content varies between 200 to 250%. What I want you to notice, the amount of soil piping through 11 of the geotextile with 7 different soil is significantly higher, okay? A lot of soil came out of that. In many applications, we don't want that to be happening, okay? So definitely water content of the soil, which was not really a part of many of the retention criteria, plays a very important role. We conducted more recently a study where we changed the water content from 230 to almost 800%. And we find that, again, water content plays important role. And in each of these cases, geotextile largest pore opening was same, okay? And we did find that O95 played important role, but it is the key message here is water content becomes a very critical factor when we are looking for soil piping. Now, let me take you to really a different application of geotextile, which is a geotextile tube. And what you see on the right-hand side are black tubes. They come in different sizes. You can make it in different sizes. And many in application, in mining application, slurries which we pump can be as low in solid content as 0.4%. And in dredging application, that can be as high as 15%, which means very high water content, okay? Now, if we take the soil, many of these soils are dredged soil and fly ash. They have very fine particles. And most of our geotextile have large openings. And these fine particles would easily come out, particularly if the water content is very high. So therefore, we modify these soil particles and we flocculate them and make them bigger flocks. So I'm going to talk about a little bit about that direction. This is my hand-drawn sketch of geotextile tube. They're dredged. I'm not going to talk about dredging. They are flocculated. Sediments are flocculated. I'm going to talk about flocculation. And then they are dewatered, means geotextile tube is working as a filter, retaining the soil particles and allow the liquid to come out, okay? And then once most of the liquid come out, which is probably water, then we worry about what we are going to do with remaining of the sediment in the tube. So these processes are in these 4 groups. Dredging, which also are making decision whether we are going to remove the coarse particles before they go to tube. Pre-treatment, which is chemical conditioning. Dewatering means what is the size of the tube, what is the type of geotextile, how much particles will be retained, and then residual flocculant and treatment. So I'm going to talk about our work in each of this category. So, and around 10 years ago, there was a wonderful graduate student, and he had a chemistry background. And we are working with a company called WaterSolve in Michigan. They have been dredging sediments from many, many lakes. So they were willing to send us 20 different types of sediments from lakes and rivers and ponds all over the Canada and US, okay? So we were very excited. These buckets came, 60, 70 buckets came, delivered. Some of them smelled terribly. So we didn't open them during the daytime. Weekend we opened and did the work in the night. These sediments were of many, many different types. And we thought we can find a relationship between physical property and chemical properties of these sediment and particles which is retained in the geotextile tube. So this student who had a very good background, he did a lot of physical testing of all the geotechnical tests you can think about, in addition to a lot of chemical tests. But we found that each sediment is so unique. There's no uniform relationship, but more of the physical properties of the soil particles and soil plays some role, little role, but every sediment was different. So learn a lesson. We are still writing this paper because we don't know how to really calibrate and come up with all of these properties. Now, chemical condition and flocculants, as I mentioned, when they are small particles, generally polymers are added in the tube. I'm going to talk about a little bit of our work in this particular area. So we conducted two studies. One, we used a polyacrylate, cationic and anionic. You can see them. There were 9 cationic polymer and 8 anionic polymer, all higher molecular weight. On the top is anionic filter cake. On the bottom, we see a cationic filter cake. Both have a very high molecular weight. And what I want you to notice that they are very different, particularly the flocks which are formed in anionic polymer. They are much larger flocks, look like a cheese curd kind of thing. And if you look at the extreme right, the geotextile, which you see is completely clean. All the particles are flocked together more like a lump. And flow rate is also different. Where cationic, which is also bridging the particle together, make a little more silt-sized flocks, and from that you see filter cake is very different. So the flow rate is very different. And we selected 4 different type of soils and performed the test. So let me show you some results. We find that polyacrylate, particularly for these 4 soils, made larger flocks generally, and where starch flocks were very small. Okay, that is one. On left-hand side, you see a result. The curve, which is really the extreme right, which is without any polymer, you see by adding any polymer, whether it's a polyacrylate or starch, the time of flow or removal of water decreased dramatically. But what is important to note, if we look at the table, without any flocculant, amount of soil passing was around 6,000 grams per meter square. By adding polyacrylate, that reduced to negligible amount. But using a starch, you still have around 400 grams per meter square, which is not much. So I think both of these polymers worked well. But what we found that the water content or solid content of the filter cake, which is very important, was much higher with starch compared to polyacrylate. So starch did work as an effective polymer, and it drained more water out of that. And since then, in many applications, we have tried to use starch instead of polyacrylate. So let me take you to performance test. And over the last 20 years, we have tried some existing tests, such as centrifuge, which is not really a typical geotechnical test, but we find it to be very effective to calculate solid content. We have developed 1D, 2D, and 3D lab tests. And then we have performed in the lab some larger tests. In fact, one of the papers presented tomorrow will be large-scale tests, which we did a few years ago. Now, what do these tests tell you, and how do they compare? Of course, when you do 1D, it's a simpler compared to 2D and 3D. So I'm going to show you some results here. What 2D test, which we have developed, it allows the water to flow vertically through geotextile and radially to geotextile. So we can look at the direction of flow and how the filter cake forms differently. Now, here are some test results for a given type of soil, 1D, 2D, and 3D. Okay, and many times in field, we do 3D test. Sometimes we do just 1D test. And the red box, which I show you here, you can see the solid content. So if we compare 1D to 2D, there is some difference. But when we see 3D, the solid content are at least 5 to 10% lower. Now, this is not always true for every soil, but this is based on many silt and clay which we have tested in the lab. Now, the liquid which comes out of the tube, sometimes polymer can come out of also. So we have developed a technique which is called streaming current method to measure amount of polymer which come out. And more recently, I was able to collaborate with a colleague in biology department to measure the toxicity of the polymer which can come out of the geotextile tube. So what I'd like you to see on the graph in the bottom, the blue bars, which are completely full bars, are 30 ppm of polyacrylate, where all the embryos died by exposure of this 30 ppm of polyacrylate, where next to that is 30 ppm of starch, where hardly any embryo died. So 30 ppm is a very high concentration. But this is important, and this was the first time we looked at the toxicity of the effluent which could be coming out of the geotextile tube. We have tried adding different type of fiber, natural fiber. In fact, one of the fiber here is a peanut shell, just ground together, coconut fiber, synthetic fiber. And what was the purpose? We wanted to see whether we can increase the strength of the filter cake, because in many applications, we stack the tube one over another. And stronger is the really material, it will be able to bear that other tubes on top of it. So now I want to talk about 3 different case histories, okay? And they are very different in terms of really the scale. First, on the left-hand side is a small industrial pond owned by a company which makes a glue. It's in Illinois. Material in this pond was really their waste. And they were running out of the capacity of this pond, and they wanted to dewater that. Okay, so that is first project. Second one, the middle is a scudder retention pond in a residential area in New York. And again, the lake was running out of the capacity. A lot of sediment were deposited, and they wanted to dredge those sediments from the lake. And third one is one of the largest projects I think ever done in Syracuse, New York. I've been living in Syracuse for 42 winters in Syracuse, New York, very much part of Onondaga Lake, which is a beautiful lake, but most contaminated lake in this country, okay? And cleaning of this lake happened by dredging the sediment, which are highly contaminated sediment, using geotextile tube. So these 3 case history, different type of project, different scale. So I'm going to walk you through some of the project, and some of the things I have mentioned about performance test and all of that, these are applied here. So first case history, I was working with a company, and they were bidding for this project. And they performed some tests in the lab, and they said that when we take these sediment out of this industrial pond and we dewater it, it will have 20 to 30% solid content, okay? There was another bid which we say the solid content will be 40%. So I worked with this company, and they said, can you do some testing in the lab and give us an idea what will be the solid content in the field, whether it's 40% or it's 20% or something else. So this is the project. We received the sample in form of a slurry, and we tried to measure the geotechnical property when you dry it, because like a little dry biscuit, you crush it, you can measure, it has no cohesion. It's not a soil, it's a gluey kind of pasty soil. We did find some polymer, synthetic polymer, which could flocculate this slurry. And then we perform 1D test and 2D test and centrifuge test on this slurry. Okay. So 2D test was very wonderful because we could see how the filter cake would be formed in radial direction and vertical direction. It looks like a blotting paper, actually. And we have developed a model based on the work done by Larson and and we use the model as well. So let me just take 2 minutes to talk about these test results. So what you see on the extreme right, my right, but your left probably, average test. So I'm going to start with PFT, 1D test. It gives you average solid content of around 18%, 18 point. Then 2D test, solid content around 22%. 3D test around 21.2%. And centrifuge test, which is a small tabletop test, around 23%. And model is around 23%. From geotechnical point of view, this data is very close, okay? They are giving us an idea of around 20 to 2%. So based on these results, we suggested to the company, your bid for that solid content in the field will be around 22, 23 is a good idea. And in fact, that's what they got the project. In the field, they tested a big tube, and solid content was around this range of 23, 24%. This was a wonderful relief. It gives an idea that some of the tests which we do work, okay? And so this is the first project where all these, which I talk about performance tests, come into the practice. So let me take you to the next project. This is not an industrial, this is residential area. And this is, around this lake, there are homes, okay? The most of the sediments going in this particular pond is really the garden soil and so on. It was tested, none of the sediments were contaminated, and it was decided to use geotextile tube to dewater these sediments. So we were involved, my student and we were involved in this project with the company who was leading this project. So we did tests in the field where the sediments are coming and being dredged, and we are doing these tests. And this particular project, we wanted to see whether starch can work, whether polyachromides. So some of the testing which we did with the starch. We brought the sample back to the lab, and buckets of sample, and we found that, as you expect, that there were little dead woods and some paper, some plants and so on. So we separated them, and then we perform different tests. Okay. So I skipped one. Now, in the field, the testing was done, which I'm going to show you. So the full tube tested done in the field gave an average solid content of around 27%. So now I'm looking at centrifuge, and it is much higher, it's 33%. And then I'm looking at 3D in the lab, it's a 36%. So unlike the first case history where everything matched beautifully, this is not the case here. And one of the possible reasons definitely is samples coming from this pond, dredge sand, were highly variable. And when we brought in the lab, we separated some of the coarse particle, so it's not really truly representative of all the sediments which go inside the tube. But it still gave us an idea that starch does work as good as the polyachromide, and that what we predict in the lab sometimes can be much higher. The design resulted in the 5 tubes, and you can think about there are only 5 tubes. But these tubes, you see a little person right there? It's a person for 5 feet, 10 inches tall man sitting right here. So these are huge tubes. And these tubes were successfully dewatered the sediment. Sediments were very clean. In fact, the residents of that area were asked to take the sediment and use it in their garden. So it was a wonderful, successful project from dewatering point of view. Now, the third case history is more of, I was a consultant, but there are companies here, Tenkate and so, who were involved in this project. So when I moved to Syracuse, my husband and I moved to Syracuse, this was a joke. If you catch a fish from the lake, you will glow because it is so contaminated, okay? For 100 years or so, lot of contaminants by industry have gone in this lake. And this is the first time in the local newspaper this article, full-page article appeared, and first time it shows where the dredging would take place, where capping will take place, what is geotextile tube. And it's interesting for me because when I moved to Syracuse, people will ask, what do you do? I said, soil dynamics, earthquake engineering. They'll say, why do we need to do that? Earthquakes don't happen in Syracuse. Now, when I say, what do you do? I say, you know Onondaga Lake, all the contaminated sediment, the tubes they use, I work in that area. So it has become much easier to explain why it's done and why I do that. So I really appreciate that project. The lake it's one of the largest dredging projects in the country at that time. All the steps I explained in my presentation, dredging, sorting, polymer collection or decision, addition, dewatering, and then finally what will happen to these tubes and what comes out of this is every step is same as a small project, except the type, here are tubes. There are almost 900, I think 94 tubes. There are 5 layers. All these contaminated sediments are permanently landfill in this particular area. And this project completed in 2017. If you go this area, we are still not allowed to go in this area, but all vegetated and it looks beautiful. So I think this is a story about geotextile tube as a filter, but with all these new strings, which is polymers and what comes out of the polymer toxicity, had made really this work exciting and challenging. So I have just 5 minutes. I'm going to talk to you a very quick journey on teaching. So I've been teaching at Syracuse University, which is a private university. It's known for its snow, and it's known for its sports, okay? I'm from a small department and of around 280 undergraduate, and there are some of them are here. And I taught my first course on designing of geosynthetics in first course in 1990, after I started working this area. Since then, I have taught this course 30 times. It takes generally graduate and undergraduate student. I introduced geosynthetics and all the wonderful samples which we get from manufacturers for K to 12. I built the models, my student and I, and demonstration. They love when you add the polymer in the slurry and flocks turns, and that is just a very likable project. I introduced geosynthetics as a manufactured material, as suggested by my friend Angel Palomino, not man-made material, but manufactured material. We introduced them right when I teach geotechnical engineering. And I think students need to see this product or materials and different variety right from the freshman class. And then geosynthetic class, which I've been teaching, is all project-based. I've been benefited by many manufacturers who have come to the class, offered training and given software. One thing which I am particularly pleased that I encourage students to build 3D models. And I am surprised, and actually, eventually they are sometimes resistant, but I'm surprised at how beautiful 3D model over the time they are built. And they work beautifully for K-12 education. And here are some of them. Now, my third strand, which is collaboration, generally we talk about service. So my research and teaching journey would have not been possible without the support of geosynthetic manufacture. In our geotechnical lab, I have rolls and rolls of geotextile, geomembranes, and in fact, variety of different products. I'm never short of it. I am very thankful for long-term collaboration with industry who have provided samples and slurries and training. Some of the manufacturers of polymers, SNF, have for last 30 years, without question, sent us a polymer, come to the lab, trained us, and then Tenkate and Husker has provided testing equipment and samples, and of course, Koerner Foundation for funding several of my graduate students, and National Science Foundation, which I've been lucky to receive funds to do research in this particular area. Now, no journey or academic journey can be wonderful without great graduate students and undergraduate students. So I can't thank them enough. It has been an exciting journey. And my last slide is about mentoring, helping, and collaboration. So I have to take you almost 30 years back when I presented my first paper at ASTM meeting. I really did not know about different type of geotextiles. So in my presentation, I misquoted a geotextile. It was non-woven, needle punch, I said something. So after my presentation, a couple of people came to me and said that you really don't know what geotextiles are, and you have a lot of learning to do. I was very disappointed. I've just started working this area. So, but there was a gentleman, and his name was Bill Hawkins. I think some of you remember that. He came to me and he said, "You have some time? I will be happy to sit down and explain to you what geotextile manufacturing is." And for 40 minutes, he sat down and explained to me. I've never forgotten that. He became wonderful collaborator. We talked, we published together. That's what I call a really true mentoring and collaboration is. I've been lucky. I have a list of people here and names who have helped when I went to their lab to copy their equipment. Sam Allen is one of them. They were gracious. PMI, whose lab I have used for 30 years, they were gracious and very, very helpful. So I think this research journey cannot be successful, enjoyable, without the support of many and all the people I have listed here. And the last 16 seconds, I need to read this. Dr. Koerner was a true leader, which all we know in geosynthetic industry, and his unwavering kindness and selfless mentoring, dedication to teaching and collaboration touched countless. And I am very fortunate I'm one of them. Thank you.